the workshop, but really Christopher has done most of the work, and thank you for including pinging me for be a co-organizer. I'm also managing the day, and I'm managing my talk in addition. So like today is really my honor. And so today is going to be slightly different. Actually, I think, especially in this talk, very different from what we have been seeing in the previous 3 days. I hope to keep you with me for the talk and then for the rest of the day. We will have theory, a bit less in this talk, but definitely theory. And but we will also have some, let's say, formulating some tasks that graph neural networks and in general machine learning, but especially with the attention to graph neural network, would be important, would be, let's say, fundamental for being able to advance in the area which I call mixed integer linear programming or mixed integer linear optimization, and I will try to be clear in a moment. So in the 3 days so far, we have heard multiple times saying, well, we can use this to solve hard combinatorial optimization problems. Yesterday, for example, and in a few other cases. And I will try to be precise on, try to jump on what it means, or at least what it means to me, and also try to be more general to understand what the influence of learning can have in discrete optimization and combinatorial optimization. So this is intended to be a step, let's say, boot camp, or I've been reminded yesterday that boot camp should be slow and boring. Not in my case, I mean, you guys have been not boring at all, but in my case, I think it's going to be boring for many of you, but I will try to really go slowly and eventually use the board a little bit. I have taken some notes and so on and so forth, but I mean, let's give it a try. So the motivation, I mean, probably not necessary, but so the use of machine learning for combinatorial optimization, and in particular for mixed integer linear programming, and give me a second and I will clarify the difference here, or at least my take, has been really like very popular in the last 10 years for sure. Of course, this is true due to the incredible success of machine learning in many areas. Deep learning has been doing, I mean, had done incredible advances in image recognition, language processing, games, and so on and so forth. Then the natural question for people in discrete optimization like me was, well, and in many other areas, was can modern statistical learning help in improving things that I'm doing in my discipline, okay? And combinatorial optimization is one of those. So what I try to do in the talk, in the boot camp, is to first to talk about mixed integer linear programming as a successful story. So I try to convince you why this is actually is a successful story at the intersection of mathematics, algorithms, and software development. There is actually a significant push on the software development side, because many of the results that have been developed in the last 70 years, roughly, are into the software, and the software is routinely used in ubiquitous to actually solve discrete optimization problems in practice. So this is the reason why we are actually keeping an eye on the software, so on the algorithmic component that is implemented into the software, and the way in which I will also try to give you, to talk about today, is the way in which we can improve such algorithms that are already in the software, or maybe even, and this is maybe the second part, how to change the software and the algorithmic component of the software in order to make it actually more effective. And we'll probably finish with some perspectives, but it's not really the big deal. So just to give you a sense, this is actually like a graph that has been developed by my friend Neil York-Smith about the various interactions between machine learning and optimization, and discrete optimization in particular. But of course, the first and most obvious connection is Many machine learning methods are using continuous optimization as a workhorse for, stochastic gradient descent as an example, and everything else in order to actually get minimizing the loss function that is behind the scene, right? And so, but nevertheless, this is actually like the most straightforward component, but everything else is connected through, indeed, this area that I will discuss today, which I call machine learning augmented combinatorial optimization. So how do you use machine learning for somehow speeding up algorithms that solve for solving combinatorial optimization problems? There's a lot going on in other areas. Will be covered today by others, and so I let them talk about that. In particular, today, and this is what I will present today is core of this is actually joint work with Lara Scavuzzo, Karen Ardal, and indeed Neil. Will be based about, how to augment the branch and bound method, which is at the core of solving discrete optimization problems by machine learning, and in particular by graph neural network, because graph neural networks have been shown to be particularly useful for that. So now, before, maybe I have a slide, just to remind us why this is actually a successful story. So routinely in telecommunication, logistics, energy, many other areas, people are using software, which can be open source, but is actually most of the time the best of the softwares are actually commercial for solving these problems, right? It's like very large scale problems. Nowadays, one can say that there's a fair chance that if you model the problem as a mixed integer linear program and you use a good software, you will get good solutions, and you will probably be able to take actions associated with the solutions that you're computing, which is, to be honest with you, I still don't believe it many times. So it's actually surprising to me, because we're talking about discrete optimization problems, we're talking about NP-hard problems. So there is actually, we don't have a provable guarantee that we can solve in any good time those instances of combinatorial optimization problems. So now, how do I do that? And this is the first catch that I would like to point out. So why do I talk about mixed integer linear programming versus combinatorial optimization? Any combinatorial optimization is a problem that has discrete variables, right? It means that some of the variables of your problem are restricted to take integer or discrete values. And then, you don't need a model for that. You can develop your own algorithm that taking into account this particular application and doing this specifically for that. When we switch thinking about mixed integer linear program is because we have in mind a very specific way of formulating the problem, just using linear inequalities, and the variables are restricted to be integer, or at least some of the variables are restricted to be integers. That's why the mixed part comes into the play, says some of the variables are continuous, some of the variables are restricted to be integer. And then at that point, the work, I'm ending up with something like this. So a formulation of that type, so which is minimizing a linear objective function characterized by the vector C, so linear weights, over a set of linear inequalities represented by this matrix A, X are my variables. Some of the X are restricted to be integer, for example, the first P variables, and the rest of the variables are continuous, okay? And this is actually all I need for defining a mixed integer linear program, which is, in a certain sense, a restriction of discrete optimization, because in discrete optimization, you don't need to do this formulation, right? You can solve your problem maybe by branch and bound, but devising some combinatorial bound that you can think of, or maybe you have no linear constraints, this still with discrete variables. I'm restricting my attention to a specific area, okay? And in particular, once I have this, and this goes back to my comment about the software, now I have a workhorse, okay? So the workhorse I'm using in discrete optimization when I'm restricting myself to mixed integer linear programming is the linear programming relaxation on this problem, right? I know that as soon as I forget about the integrality requirement here, and I relax it to be a continuous variable, the associated problem becomes easy. I mean, now this means really easy in the sense that from both a theory and practical standpoint, it becomes a linear program, and I can solve this linear program in polynomial time, okay? So the LP relaxation, linear programming relaxation, is my workhorse. And the software that is implemented for solving these problems is actually like, you can think about it as a game in which you win if you solve a limited number of linear programming relaxations, okay? The smallest number of linear programming relaxation you solve, the better, and you're going to be converging fast to the optimal solution, okay? That's the game I want to play. And the game I'm playing, I do it by in a surprisingly easy way, thanks to my colleague and friend Elias Khalil. I can represent the entire thing in one slide that does the following. I'm saying, okay, remember, I'm minimizing a linear objective function over this set, and I can build this red trajectory that is the primal trajectory, so solutions which are feasible for this problem, so which variables are mixed integers, some of them are integer and some of them are continuous, and every time I make an improvement, I actually go down in the trajectory, and at the same time, I'm building a dual trajectory. Using linear programming duality, I'm solving the LP relaxation of the problem, which is actually here. So if assuming that, which I don't know, this is the optimal solution, this is actually, of course, an optimistic approximation over the value of the optimal solution. It's a dual bound, so I'm sitting here. It cannot be better than that. And then I build another trajectory, the dual trajectory, that is actually deteriorates this bound slowly, in a certain sense, and as soon as the two trajectories intersect, then I'm happy and I can prove optimality, okay? So that's the game we're going to play, and the point is to get here in the smallest number of iterations possible, where, roughly speaking, an iteration for me is solving an LP relaxation, okay? If I'm doing this fast, so with a small number of LPs, my algorithm converges in, let's say, something that is similar to a polynomial time. Otherwise, if the number, of course, this process can be exponential. I go to exponential number of LPs, then I'm not going to be efficient in solving the problem, okay? And the way, and at any point in time, I can measure the gap, so I have some sort of guarantee on what I'm doing, because the difference between the current best primal solution and the current best dual solution, or worse in a certain sense, dual solution gives me how far away, gives me a pessimistic approximation on how far away I am from the optimal solution, okay? And the way in which this is done is called branch and bound. So what I'm doing is, how do I build, so the red trajectory, we can think about anything, right? I mean, you can have your own favorite heuristic that is producing feasible solutions. It would be good that is connected to the LP relaxation in some form, but it doesn't matter. Here, instead, how do I go from here to there? The idea is divide and conquer, very easy. So I solve this LP relaxation. I end up with some variable up there that is takes a fractional value, so continuous value, but it's supposed to take an integer value. Let's assume that, for example, is a binary variable, x2 here, has taken 0.29. And then what I'm telling myself is that the 0.29 is not possible, so either it is 0, and then I can add to my relaxation, to my problem, another constraint that forces the variable x2 to be 0, or it must be 1. There is no alternative, and so I split my problem into two subproblems, and those two subproblems one of the two will contain the optimal solution. Okay, and I can keep going like this. This is called branching. And of course, the bounding component is associated with solving the LP relaxation. I compute a bound over how good I can be in that subtree defined by this branching. And if this bound is already worse than the current solution I have, I can fathom the subtree. I can throw it away, and so I do an implicit enumeration. I don't do the full enumeration of the problem. Once again, this is boring, of course, for many of you. This is really like a one-on-one integer optimization, but I think it's important because I will talk about what is behind the scenes, so internal to this simple algorithm, right? So the dual bound, the blue trajectory here, is that at any point in time, I take a picture of my tree, and with all the open nodes that define this frontier, the one that has the worst bound, or the best in a certain sense, or the one that in which I could reach the better solution, so the one that is lowest, gives me a point here in this trajectory, okay? And this point in the trajectory, together with the point at the same time in the red trajectory, is giving me the gap, which is let's say the standard way of I'm evaluating the quality of what I'm doing. Okay? Questions, comments? Again, boring, but important. So what is behind the scene of this simple algorithm? The algorithm is, this is let's say the current generation of MIP solvers. So the beginning of let's say integer programming is rooted to the work of Ralph Gomory in 1958, the first algorithm to solve integer programs by cutting planes, by the way, which I introduce in a second. But somehow 1958 is the birth date of integer programming in a certain sense, and from that on there have been like multiple attempts to get into like routinely solving those problems. The current generation of solvers which are implementing the branch, let's say, a clever modification of the integer of this branch and bound is you can imagine that split in 4 building blocks. The first one is called what I call preprocessing or configuration, which means whatever you do at the beginning to actually preprocess your instance and deciding how to actually solve it afterwards. Then there is a phase in which the solver is, and the algorithm behind the scene. I use solver and I'm using technology, MIP technology is more or less the same way, because the way in which the solvers are implemented is no magic. There's essentially following these recipes in a clever way and in a very, very sophisticated software engineering way, okay? So now, what do you do? This phase you can imagine is like a cleaning up, but also a phase in which you try to strengthen the relaxation. Because once again, the game we want to play is reducing the number of LPs as much as possible. So if in the picture that I gave you before, which I have to rebuild, if I'm sitting here, I have a significant distance to go there, right? It doesn't mean that it's going to take too long, because maybe every step will be effective, but it's far in a certain sense, right? If my LP relaxation was already here, let's say very close to the optimal solution, well, intuitively, we're going to be faster to converge to that. It's not always the case. There are the so-called primal problems in which the LP relaxation coincides with the integer solution, but it's actually a pain to get there in any case. But let's say, on average, the closest you are to the optimal solution with the LP relaxation, the faster you should be able to converge to it, okay? So whatever I do here, before starting the real algorithm, the branch and bound algorithm, in order to actually to pump up this relaxation closer to the optimal solution, I should do. And in addition, even in a more sophisticated way, I can do this by tightening the LP relaxation. So AX less or equal than B is the constraint matrix. I can add additional linear inequalities that are actually raising this relaxation, up to close to the optimal solution. Why? Because they are cutting off part of the solution space which do not contain the optimal solution. And I'll be more clear in a moment. Sophisticated branching, so I needed to split the problem at some point, and I want to do it in a clever way. And of course, the red trajectory is how do I get there, right? I mean, how do I produce feasible solutions of my problem in such a way that I'm converging fast? In theory, I don't need it, right? I mean, it's like, if I'm good enough with the blue trajectory, I will build an integer solution with the value of the optimal solution, and so I don't need anything else, but that's going to be too slow from a practical standpoint. So now, before going into the details of these 4 building blocks, is a boot camp, so I'm allowed to go into the details, more or less. The question, however, I would like to clarify is, so what do I mean with solve a discrete optimization problem or a mixed integer linear program, right? Here, this has been used, solve combinatorial optimization in these 3 days occasionally. But I kept asking myself, and when I was preparing this talk, it's like, what do we mean here? Okay? So, of course, you can think about machine learning substituting this everything here and say, well, I want to learn the optimal solution value of my integer program. Or I want to learn the optimal solution, so the value of the variables of my integer program. I can do many other things. My take, and the way in which I will talk from now on, is instead not replacing discrete optimization, so not replacing the branch and bound method, but try to make it more efficient, okay? So that's why I deep dive in, as much as possible, of course, in these 4 blocks and say, well, which are the questions? So what are the tasks that learning can help for in order to actually speed up the computation here? And note that even if the algorithm can be described in one single slide, catchy way of seeing these 2 trajectories, the branch and bound algorithm is a combination of, let's say, millions of decisions that one has to make, and some of which are, let's say, we don't understand mathematically very well, or some of them are very, let's say, there are a lot of ties that I should break in some principled way, especially if I have data to actually do that, okay? So, my take, and again, this is not to put down alternatives like using learning directly to get the solution of an integer program. My take here is to actually help integer program to get those solutions, but not replacing them. And actually, let me say, why is this my take there? You can say, well, you did for 25 years integer programming, so now you still want to reuse it, and that's true, partially true. But my take is, so learning, these are NPR problems, and learning will give you a statistical tool to compute approximate solutions of those problems, like maybe with a good guarantee in some particular circumstances, but I mean, it's like it's still approximate solutions. My personal experience in all this time is we are pretty good in producing approximate solutions. So there's a bunch of alternatives producing approximate solutions, but producing optimal solutions has still a lot of value. And producing solutions with a gap guarantee also has a lot of value. And so somehow this is the way in which I will give you the intuition today. So coming back to the deep dive, so preprocessing, I said it a little bit, is that detect certain changes in the input or configure the algorithm so as to likely obtain a better performance for the algorithm itself, right? I mean, catching some structure in the problem. I mean, in the way in which I described the problem, I'm not using any structure in A, but that's not really true. I mean, if I catch some of the structure by, analyzing the problem, of course I know that for a particular structure on a matrix A, some tools will be better than other tools, and I can configure my algorithm to actually work in that way. And this is actually what is done in the pre-processing phase. And actually, this is the area in which currently we have the most success. So far, we have shown, advances potentially in all the 4 blocks that I'm talking about, but the advances that we have obtained in this area of preprocessing, and I will be detailed at the end of the presentation, are the ones that are in software production. Stephanie.
What exactly did you mean by changes in the input? This is for the different LPs?
That's a good question. So changes in the input could be, for example, strengthening the bounds of the variables, or removing constraints which are dominated and stuff. Removing constraints, dominated constraints, is a cleanup, but sometimes I can analyze. For example, I can find clicks in my graph. I can build a graph. Let's say I realize that there are clicks, and then I can strengthen the constraint by lifting variables in or reducing the bounds of the variables. That's the type of input that I have in mind. So what are cutting planes? So again, pictorially speaking, this is assume that we are on R2, or this point, the blue points here that are inside this blue area. These are the feasible solutions of my problem, right? I mean, if it is a pure integer program, these are the only points. And this explains quickly the difficulty, right? I mean, this is not a convex set anymore. It actually is a lattice. And so this is the problem we're getting from one point to another. So when I solve the LP relaxation, I actually give up looking for those points. And I'm saying I'm looking at a convex region, actually, in this case, a polyhedron, that actually contains all the integer points that I care about. And I'm assuming this is the optimal solution of my LP relaxation. So now, what I can do is that I can generate linear inequalities to append to my system AX less or equal than B, in order to actually, that have this property, which is called separation. They separate the fractional solution from the set of integer solution. The set of integer solution, you can, in this case, you can imagine this is the convex solve of integer solutions. So the smallest set containing only integer solutions, and which means that the corners of this set are integer solutions. And then if I'm able to actually use this procedure, generating cutting planes in an effective way, I will be able to strengthen the LP relaxation. And eventually, the idea is to strengthen this LP relaxation close to the optimal side, so where the objective function is pushing me, right? I mean, because, I can clean up this area, but it's unlikely going to be useful for converging to the optimal solution, okay? So now, the software, your favorite MIP software here has many families of cutting planes or cuts that belong to this arsenal, and surprisingly, they pretty much all work in a relatively simple way. You take your system AX equal to B, less or equal to B or whatever, and then you collapse it into one single called base inequality by aggregation. You do some sort of aggregation. And at that point, you apply the fact that some of the variables are needed to be integer. So there is an integer rounding argument that allows you to generate an inequality, which is a cutting plane. Okay? The reason why 1958 is considered the birth of integer programming is because Ralph Gomory told us how to do this in a very efficient way. You solve the LP relaxation, you read from you read the inverse of the basis of the simplex that the simplex method automatically gives you. This is the set of coefficients that you need to do this aggregation, and then you just round the corresponding inequality, and you get an inequality which is violated by the fractional solution that you have obtained at the end of the simplex method. Very, very, very straightforward. It's not enough. You need a little bit more than that in order to actually get a very good cutting plane algorithm to converge fast, and not only in theory, but I mean, this is actually the core of what we are doing. And but immediately it tells you, well, there are a lot of constraints like this. I can generate a huge number of constraints, and the point is, I cannot afford to just dump them all, increase AX less or equal than B too much, because the problem is that if I do that, there are two significant drawbacks. The first one is, yes, I can solve efficiently linear programming, but still, I mean, polynomial in the size of the problem, right? I mean, if I push the size of the problem too large, then the LPs will be difficult to solve. But even more, which is the problematic component, I keep adding inequalities in a specific area, right? I mean, around here, which makes the numerical stability of the method very shaky. So I keep adding corners of this polyhedron, one very close to the other, and those corners are actually leading to numerical instability, because the simplex method has to pivot over those, and so on and so forth. It's becoming quite a complicated thing. Okay? So the takeaway message is cutting plane is a terrific way of actually strengthening your LP relaxation. The problem is that you need to find a good compromise on how many of them do you add, which of them you add, and which are the effective ones, and so on and so forth. Branching. So how do I gave an example before. I said the variable is, the x2 variable was equal to 0.29, so it cannot be true, so either is 0 or 1. More generally, an integer, a variable that is supposed to take an integer value, if the solution of the LP relaxation gives me a fractional value instead, then I can round the variable down and round the variable up, and I'm just saying that I split my domain into two subdomains in which either the variable is less or equal to the rounded down value or greater or equal to the rounded up. Okay? This is trivial, but has significant, let's say, consequences in what you're doing. So, of course, on the one side, you are chopping off areas of your relaxation, right? I mean, I'm chopping off this part and I create these two polytopes. I'm chopping off the other part and creating these two polytopes. But which, in the attempt of saying, well, I go smaller and smaller, eventually I'm going to get integral, right? I mean, it's like at a certain point I will go converge there. The problem is the following. We don't have a good mathematical understanding of how to do this in the best possible way, and we don't even know how to define best possible way. So it's actually the number of nodes that you produce in this branch and bound. So it's actually a bit of some complicated questions. I mean, the takeaway message here is if I branch on a variable, so I decide to branch on a particular variable and there is no effect, so somehow both polyhedra that I'm producing are polytopes I'm producing, or polyhedra in the case that one part is unbounded, didn't bring it any improvement to what I had before. I just duplicate the size of my branch and bound without any effect. And this actually can be terribly bad for the game that I want to play, so which converging to the optimal solution as with the smallest number of LPs. So currently the best method we know is called strong branching, and does something very trivial. So takes any variable which is supposed to be integer but is fractional, and branches, simulates branching on that particular variable, computes a score to let's say capture the quality of the branching, in the sense of saying how good I move away from the current point, and then picks the variable that is giving the best score. So now, why this is bad? Because this is too expensive. So I'm thinking about solving problems with thousands of variables, or if not 100,000 of variables. At every fraction, at every node in this branch and bound, there will probably be tens of thousands of variables which are actually fractional. So solving LPs is fast, but simulating the branching leads to actually just too many LPs, and the game that I want to play is still not efficient anymore. So questions behind the scene. Finally, heuristics, primal heuristics. So the attention to the primal heuristics started roughly, let's say, 20 years ago. The point is, it took a while to get to a point in which the MIP solvers were effective to solve problems, and at that point, the practitioners started to ask, well, should we converge to solutions faster than just waiting at the very end? When I was a student, I was running Cplex at the time, Cplex 3.0, which was the standard for that. You could push the button for solving a MIP, then go in coffee, and the column that was the column populating the primal part, so the red trajectory, was actually populating very, very late after you coming back to coffee, and so on and so forth. So this is the work that has been done. The good point is that now we have primal heuristics which are very good, so they converge to feasible solutions, good quality, very fast. The difficulty is proving optimality, but we have many of them, and once again, the point is that which one are the most effective for my particular problem is a question mark that we don't fully understand. So now, let me say, what is the opportunity that 10 years ago, more or less, people started to see in this area for machine learning? The first one is, we have experts, so let's assume that we have a mathematical knowledge of each one of these small components that I quickly described today. But that will allow us to make decisions in an effective way. But maybe sometimes these experts are very, very expensive. So it takes a while to compute even a simple decision that could be like 1 over a myriad of decisions that is actually made in a branch and bound. So you have to be with me in imagining that since I'm solving an NPR problem and I want to give provable guarantees of the optimal solution, it may be that the branch and bound approach takes millions of nodes, right? And this is going to be a good case. So I'm able to solve a very large integer program in millions of nodes, which is a reasonable amount of nodes. But this means that these millions of nodes internally have to solve make a huge amount of decisions, which are, each of them, I cannot take too much time to make. Okay? So the other part is that, as I anticipated, there are some components in which we have a principled way of avoiding to make mistakes, but we don't have a mathematical characterization what's best, right? I mean, it's like, we don't make such a decision with saying, well, this is precisely the thing that is going to bring me to solve the problem faster. Because if we knew that, of course, the situation would be that we probably have a polynomial time algorithm. We don't, okay? So these are the two questions, and I think a variable selection in branching is capturing both of them at the same time. So in branching, not only I don't know how to characterize what is the best branching to make, because if I knew, imagine that I know how to build the tree in the best possible way, well, I will be done, right? I mean, it's like I can do it polynomial size. I don't know that, but in addition, the best heuristic I have is so expensive that I cannot run it full size. I mean, I cannot afford solving tens of thousands of LPs just for deciding each variable, because the problem is that in any case, it's gonna take millions of nodes. So that's probably that single decision is not so important. So I cannot really afford to take so much time. So the variable selection in branch and bound, so deciding which other variable I want to branch on, is actually capturing both areas in a very clean way. However, the question became, so can machine learning, imitation learning, reinforcement learning, and powerful deep learning methods, architecture like graph neural network, help combinatorial optimization and particularly mixed integer linear programming algorithm to deal with these two issues? So being too slow or too heuristic, right? I mean, it's like finding a better, more principled way of doing things. With the catch that we want to keep feasibility, producing feasible solutions, and we want to, I mean, sometimes in a certain sense point, it's like I don't want to break the algorithm. The algorithm, if I give enough time, my branch and bound should still converge to the optimal solution. So the choices I'm making using graph neural networks, for example, they should not impact my ability of converging to the optimal solution if I give enough time. Okay? So, which is, I mean, on the one side is, for people like me, is an obvious requirement, but clearly not obvious if you are thinking about statistical learning and you want to approximate things. Of course, there are two ways that the literature has been evolving. And one is a demonstration. So what do you do? I mean, every time I make a decision, I have an action, and I have an expert that knows how to do this action. And I can try to minimize the distance, so the loss function between those things, and doing some sort of imitation learning. So I know the expert that makes maybe it takes too much time to actually follow, and I can try to approximate the expert in a fast way, producing an approximation fast, and speeding up the process in the case the situation is too long. Okay? And here there's a bunch of methods, some of them I will talk about, that in particular graph neural network came into the play here to actually do a significant breakthrough for some of these problems, in which you know the expert, at least you know an expert which is actually very effective in practice, branching, so the strong branching. But you cannot afford to actually run the expert all the time. Of course, the alternative would be to try to learn by experience in a certain sense. So you make an action, you compute a reward, and then, I mean, somehow you are you're maximizing the return of this. So by demonstration, of course, or imitation, you are restricted to the quality of the expert that you are working with. Instead, if you are applying experience here in this way, so like, which of course recalls for reinforcement learning, calls for responsive learning, I will be able to go beyond the expert and potentially actually getting farther away in places in which I don't even know exactly what is going to be the best thing to do. So far, we have been reinforcement learning has had some significant success in the area that I'm not covering today of producing good feasible solutions for integer programs. But inside, let's say, for improving or speeding up the computation inside a branch and bound, there is less obvious successes. Yes, question.
So it's a very basic question, but basically the goal here is that you will be okay to lose a little bit of optimality if you gain a lot of, if it's much faster, right? In these cases. Or what is the kind of, what would be a success?
A success would be to, depending on which expert, for example, coming back to this point here. So assume that the expert, if the expert is telling you, oh, this is the only thing that you can do to guarantee optimality, I cannot afford losing it. Okay? I cannot approximate that expert. But if the expert is saying, well, this is the best variable to branch on, but note that the point is, in branching, there is no mistake. You are enumerating the worst case scenarios that you're enumerating the entire tree. You're not getting. You are you're still converging to the optimal solution, right? You're just converging slower. So if I'm able to branch on a variable which is maybe not the best, but the second best or something like this, maybe I will lose a little bit, but I gain the time it takes to actually make that decision. And overall, it's going to be a success in any case, okay? So the type, I mean, then we can, of course, we can say, I'm also happy to speed up the process and losing 5% optimality, but this is not covered here, okay? I mean, but yes, in theory, yes, but this was my point with this thing. So I can say, I definitely don't want to lose feasibility, but I can maybe even producing an approximate branch and bound approach, maybe that's okay, except that I need to know that, right? I mean, it's like I cannot tell you that this is actually, for example, I can imagine saying, I can imagine in a branch and bound framework like this, saying, okay, I can try to learn the solution of this node before deciding if exploring it. And if the solution is not good enough, I can kill the node, right? I mean, I can kill the subtree generated by the node. That one will lead to an approximate branch and bound approach. Maybe that's good enough in some circumstances. I will not cover stuff like this, but it's actually like, it can be good enough. Okay? Yes?
Maybe you're going to talk about it later, but in the next slide, is your ML emulator, or the expert, are they dependent on the problem? Or like, I'm thinking about whether you're going to do this emulation per problem, or you actually do it like for a broad class of problems.
I will essentially spend the rest of the time talking about this.
Awesome, thank you.
But of course, no. Actually, that's a very natural and a very, very good question. So now, this is not useful, but I mean, just to remind us, the learning process in itself is an inexact optimization to be done with a sequence of steps, but it doesn't really matter here. So the real question that I think is actually relevant for this audience, and sorry if I kept you 50 minutes away for that, but is how do I do even represent my problem, right? I mean, because this is a MIP, and I mean, this is the way in which I like to represent it. But this is actually giving any good information for, I mean, like taking any of the tasks that I briefly, let's say, I briefly sketched before. So maybe I want to go to a neural network, but how do I go from there to the neural network? And so, I mean, this is not necessarily a good fit for machine learning methods. Think about the matrix representation or anything like this. And this is where, I mean, and then of course there are some properties that we would like to go from for representing the problem in machine learning ways, and in order to learn some tasks, to take some tasks on that side. So we want to do permutation invariance. So for example, like actually mixed integer linear programming algorithms are not permutation invariant, okay? Which is actually shocking for many of us. So if I permute the rows and the columns in my problem, and I run my favorite solver on the same machine and same configuration and so on and so forth, it's going to give me a different, not a different solution. So, I mean, the optimal solution value will be the same, for sure. The optimal solution may be different because they're equivalents. The running time of this could be astronomically different. Okay? Can be converging in one side in 10 nodes, and on the other side is going to take like 10 million nodes. Okay? Which is, I mean, I'm taking some extremes. Of course, the instances have to be a little bit strange, but this can happen. And actually, differences in the running time due to permutations of the rows and columns is actually like a very common situation. Actually, the way in which the solvers are actually playing with this is indeed doing something similar to that. So this shows, in a certain sense, that there is a lot to gain because the integer programming community has done incredible things. I mean, I still, as I said at the beginning, I still surprised that we can solve problems like that, and routinely. But the point is that statistically speaking, we're not probably the best people to actually take advantage of many things. So you want to scale invariance. The problem is that on this, some of the constraints may have coefficients of very large size, some of the constraints of very small sizes. The MIP solvers are playing a little bit of game in order to making things homogeneous, but not always the case. Of course, there is the size invariance, which comes back to all the discussion of yesterday, and on which I spend a significant amount of time on generalization, so size generalization. And of course, they need to be low computationally intensive, otherwise, the entire framework breaks down. Because depending on where you want to learn, maybe if you want to learn once at the beginning of the process, in the pre-processing phases, you can afford to spend a little bit of time. If you want to learn at every node of the branch and bound, once again, you cannot afford to spend too much time. So there are three ways in which the last 10 years the literature has been evolving on representing MIPS. And the one that is more relevant for this audience is the second one I'm talking about in a second. But essentially, you can think about these three things. So you can use the descriptors, so some kind of fixed size vectors that are representing the characteristic of the problem by doing some aggregation of coefficients, computing mean, max, and so on and so forth. And then you have some representation which is static, and this is going to be working from that point on. Fast, relatively low computationally, and in a certain sense preserves a lot of the four characteristics I was thinking about before, but somehow you are doing really a big aggregation. In this paper by my former student Giulia Zarpellon, there is a different approach, which is let's not consider really the representation of the problem of the instance that we are solving. So I'm solving this particular problem or class of instances or instance. Let's look instead at what we can collect from the branch and bound tree. So let's try to learn if my run is going well, right? It's like what did I learn so far from the branch and bound that is going to be helping me in actually speeding up the process? For this particular instance, if I do it online, or for a class of instances by doing it offline, okay? But the one that I will spend more time here is the one of using the graph neural network. This is just telling us these three methods how to they leverage the various characteristics. But how do I use? Yes, sorry.
For the last approach, when you observe store some historical information of the branch and bound tree, is that the entire tree being stored, or only some summary of that?
It's some summary of the tree of the branch and bound approach until that, which is actually. In my mind, this is actually going for more better for online, even if that paper was written actually offline. So yeah, you analyze the branch and bound trees of some class of instances, and then you try to learn which are characteristic of the variables or other things that you can learn later on. But yes, of course, part of it. Yes.
So in the properties slide, you said that it has to be permutation invariant, but then you said that MILP is not actually permutation invariant. So why would you want permutation invariant? So if you have the wrong configuration in the beginning, wouldn't you want your ML algorithm to get you to the right configuration?
That's a good point. So as usual, there is no wrong or good configuration. The problem is that you break ties in a pseudo-random way, and breaking ties means that. One of the classical problems. This phenomenon is called in integer programming a performance variability. So you're running the same instance in two different, with the, let's say, with the small the change that should be neutral with respect to what you're doing, and this is not neutral. And the reason, for example, it can be like this. So one of the things that we're not able to explain is when you solve the LP relaxation of the problem, it's very likely, because the class of instances we're talking about are degenerate, means that you have a lot of optimal solutions in your current phase of the LP relaxation. So there are many solutions. So if you pick one solution, you start adding cutting planes or branching from there, you may be lucky and you converge to a good primal and dual bound, and you converge very quickly. Instead, you can, by random noise, ending up in a different LP relaxation, which is not to, I mean, the same value, but is not good enough, let's say, in a certain sense. So you are unlucky in the rest of the process. So it's not about the quality, but it's about the process that relatively after comes in. So now, you're right. Maybe not a big characteristic, but if you are able to break some of these issues by actually learning in a principled way, in permutation invariant way, I think you gain a lot, because to reduce this variability even a priori. Okay? So it's something that will actually help us, integer programmers, actually to make better decisions internally. So, what is the representation? So let me break down AX less or equal than B, right? I mean, AX less or equal than B is exactly this. So this is my objective function, but I don't care. Let's look at the constraints. Every constraint is exactly like one linear inequality and less or equal than B. So A are all the coefficients on the n variables, okay? So I can represent this with a graph very easily. I'm saying that it's a bipartite graph in which on the one side I have the variables here. Actually, on the one side I have the constraints in this representation. So I have the constraints and I have a link. Of course, it's a bipartite graph, so the constraints don't talk to each other. The variables don't talk to each other except that they talk to the constraints in which they belong. And so they determine, there is actually like the concept of neighborhood is created by the fact that the variable belongs to several constraints. Okay? Yes?
I have a question. So where do the objective coefficients and the right-hand sides go in this representation?
They go on the vector associated to the nodes. So the feature vector associated to the variables, for example, is actually contained in the coefficient in the objective function and various other things that you can think of. For example, the LP value in the LP relaxation. So, very easy representation, which can immediately, now is a graph, and immediately reminds you, of course, let's go back for a second. So graphs are, you can represent a lot of combinatorial optimization problems by graphs, right? The incidence matrices of graphs are, many of the A matrices are incident matrices of a graph, plus many other things. But this is independent of the class of instances that you're talking about. Here is really like thinking about any integer program written in AX less or equal than B as a graph, and a bipartite graph, and this graph clearly immediately tells us, well, I can do graph neural network on this. Okay? I can build a graph neural network which actually these characteristics, and this is, since everybody did it, I have my own definition of the graph neural network, which I'm not going to go through, but essentially has the component that we've been discussing for 3 days. So this is actually like, what is actually very powerful here? Powerful is that, and the graph neural network has been introduced for branching purposes in particular at the very beginning. It tells you, well, this guy here is connected to the other guys, and if I branch on that particular variable, well, eventually I have certain influence on several constraints. What is the influence? Well, the embedding and, of course, the recursive operations should be learning the quality of this branching in a certain way. Okay? But this is actually in a certain sense, at least, and I'm still trying to round my mind around it, the graph representation is highlighting all these connections that should be important for many characteristics that we care about in the decisions to be made in the branch in a branch and bound approach. And I mean, such a representation in the paper by Maxime and co-authors is, I mean, giving a lot of implicit things, even if you're not really like considering the constraint coefficient statistics, but actually you are considering them as features of your graph. So now, I have time, but I mean, this is a, there are a number of, okay, so what I will do here is do the following. So I go back to the 4 building blocks, and I'm saying, well, where, I can tell you where and how those tasks, learning tasks have been taken. I'm going to relatively fast on the primal side and concentrate more on the branching, because this is where the graph neural network being used, and I want to talk about the generalization. But let's say primal heuristics. So a large chunk of the primal heuristics that are working well in the MIP solvers are in this family of called the large neighborhood search algorithms, which are essentially doing the following. So you take a solution, you freeze part of the solution, and you actually even run the MIP solver recursively on the rest of the solution in order to see if you can improve the solution itself, right? So large is a neighborhood because you have frozen some part of the solution, but it's large because you cannot just enumerate all the solutions, you just do it with a MIP solver. So this has been, there are a lot of methods which have been used in order to do that, to decide which part to freeze, and eventually vice versa, which parts to, how many variables and which variable you want to take into account once again. So together with Christopher, we had a paper in which we are using the graph neural network to learn in general about many things, so like doing some sort of using a same model in order to later on doing more tasks, and for example, we use it for actually like a heuristic of this type. Yes?
Quick question. This is really interesting. So could you go back to the predictions that you were making?
Yes.
So these are predictions from the nodes of the graph neural network.
These are predictions for the variables, yes.
Well, yeah.
Yes, switching the nodes, yes.
Okay.
Binary variables in
Okay.
particular in this case, yes.
So I think one thing that could be proved is that these are marginal predictors. They're not joint predictors. So you end up not predicting them jointly properly. So the constraints are violated because they are not jointly predicting what they should predict. So maybe changing the equivariances of the neural network could help.
Yeah, sure. I'm sure that there are plenty of things that can be done for that, yes. So yeah, I mean, the way in which we are patching the situation is that we are independently predicting those variables, assuming that the structure is preserved at least approximately because of the neural network. But then we are patching this by solving a MIP, right? I mean, so in a certain sense, we are saying, well, maybe we're not going to be successful, but I know I give you an input configuration that could be potentially good. But sure, yes, that's true. We are actually independently looking at that. So there is another interesting area that is called, about scheduling heuristics, but I will skip about it. So branching, variable selection. So this is by far the area in which there have been more work in total. So back in, I think 2000 and I mean, at the early 2010, we starting to actually look at, the question was, can we approximate strong branching by using machine learning, right? I mean, that was the idea. So launch a group, I mean, this was the first papers into NeoRIPS coming from the integer programming community that eventually has been established itself as an area in the big sea in the big ocean of NeoRIPS, a tiny island there, but still more established now. And so you can you can actually put a lot of those methods in here. Some of them we're doing online, so there is actually some of them are actually most of them are offline, supervised learning. There is actually some attempts on reinforcement learning recently. The breakthrough indeed has been this paper that I was talking about, which has been the one using graph neural networks. And so what it does is that use a GNN to imitate strong branching by behavioral cloning. So essentially it means that the actual variable scores, you don't try to predict the scores, but you try to predict the order in which, or at least predict the variable that is going to bring you the best, right? And the breakthrough has been the fact that in all the papers before that, the game that they were playing was, can we beat full strong branching? So you take the worst case, so you just run a strong branching on every variable. Of course, it takes a huge amount of time. Here, you are reducing time and more or less you gain. Not particularly, I mean, good for the time, not particularly from an integer programming perspective, not very surprising. That paper shows that you can beat the current best algorithms for branching by doing this, with a couple of caveats that I will discuss in a second. So reliability branching is essentially what is implemented into the solver. So you run strong branching at the beginning for a while until what is called pseudo costs become reliable. Pseudo costs are essentially you evaluate the quality of the improvement that you made by branching on that particular variable, you store it and you average it over time. And if you run strong branching for a little while, you populate the pseudo cost, and then when they become reliable according to some parameter, you say, well, I will stop doing strong branching from now on, and I will continue this way. And this is actually the best implemented into the solver with some additional perks, bells and whistles around, but and predicting over using a GNN is actually giving better results than this. So, what are the catches, however? Two catches that I said before. So the first one is a technological catch. In order to do that, I have to go to actually even, I pre-train things, but the neural network is going to be on a GPU, and then the entire thing here is run, MIP solvers are run on CPUs. So I cannot afford to go back and forth from GPU to CPU too much. And this is the part in which we are cheating a little bit, in the sense in that paper we're not considering that part fully. Of course, you can imagine that the size of the message passing may be small, so you don't do many iterations. Later on, we wrote a paper in which we're saying, well, we do this only at the root node, and then at the beginning of the branch and bound, and then after that we replace it with some cheaper and CPU-based machine learning components. This is actually working more or less, but this is one of the issues that prevents so far the MIP, mixed integer linear programming developers, so the companies that have software, to actually go that way, right? I mean, it's like the interaction CPU-GPU. But the biggest one is this, so generalization. So now, what is this generalization when we've been talking about this offline in this meeting a lot? So what do I mean here with this fail to generalize? So the results of the paper in 2019, the NeurIPS paper in 2019, are by training the neural network independently on set covering instances, capacitated facility location instances. You have to retrain the instances completely. MIP solvers are not like this. They receive an instance, they solve it like it as is. So you cannot pre-train, you cannot use a pre-trained network unless you know that that particular instance belongs to a certain family, okay? Which is a big failure, of course. So now, is it even so? Now, in terms of yesterday, we talked a lot about the generalization between in sizes. So my recollection of the 2019 paper is that we have a significant. We don't deteriorate very much if we go from small to relatively large. Now, if we go to very, very large, we didn't try, to be honest, but let's say going from small to relatively large was fine. Because around the particular class of problems that we are thinking about, so the set covering instances, we were using the same generator to actually produce the problems, right? I mean, all the problems belonging to the same class, not only to the same class, but the graph structure behind the scene was actually very similar. So my point of view here is maybe you need more in the sense that the question could be, we can stay in the same, so there's the communication here, what I want to communicate is this. When we talk about the size of the instances, and so generalization of a size, I think we have to, in integer program, there is an additional layer that is about the class of instances. We cannot talk about MIP as a whole, because this matrix that I was talking about before, that would be completely different, right? I mean, and I will get into that in a second. So then I think there is an additional layer, which is, I'm thinking about mixed integer linear programs. I mean, I think about classes of mixed integer linear programs. So traveling salesman problem, capacitated facility location, class, and then I have a class. And inside the class, if you are using the same structure to generate the problem, I think the small to large, it's not a big issue. But I can change the characteristics of this class. I mean, I can think about a traveling salesman with Manhattan distance versus something completely different. And that, I think, it's going to be potentially difficult to generalize. Yes?
Just to clarify
yes.
the difference. So does it mean that I will see one kind of bipartite graph for one class of problem, and then let's say traveling salesman problem would give me a different bipartite graph than the set covering, or
yes, completely different.
Right.
Completely different. Think about. Let me jump ahead for my. So this is it's another interesting fact. If I generate, it's very well known as folklore. I was trying to think about a paper telling this yesterday talking to Christopher, but I don't have one on top of my mind. But we all know that if I generate a random matrix in integer programming is trivial. If I generate a random problem in which the variables are not very interconnected to each other, branch and bound is going to be a killer, because you branch on a variable, immediately you put away in the next couple of nodes everything that is connected, and then you move on to something else, and then in a few hundred of nodes you solve everything. Okay? So the difficulty is that the metrics are not looking like that. So they're not random IID coefficients. They look like this. So this is a scheduling instance, and all the scheduling instances, they actually look like that. I mean, not all the scheduling instances of that particular family, they look like that. So you can think about it random, but it's not random, right? Really, like, has a very clear characteristics. This is actually the so-called linking constraints from one area to another. There is a lot going on here and there and so on. So now, I think it partially tells you, so the family will look similar to this. And then the bipartite graph with the part that I think is very strong for branching is that it captures this locality and these neighbors that tells me, oh, if I branch on these variables, the effect of the branching is going to be on those constraints. And those constraints are maybe the difficult part of the problem, so why don't I do this first? That's my intuition behind it. So now instead on those kind of things, it's like this is going to be similar, but if the scheduling instance comes from a different configuration, that will remind this, but will probably be different, and that will be outside of the distribution, even in the same class, right? And then I feel like the generalization will be harder to obtain. Okay.
Quick clarification.
Yes.
These are the A's. What are
This is the A matrix, and I have a point if there is actually a coefficient, right?
Right.
Then I needed to go to the bipartite graph, but you can imagine
right,
everything.
right. So the edge weights, basically. Thank you.
Yes.
So just to be sure, this is a case in which the graph neural network approach works, the one to the right.
Yeah, this is actually works. I mean, and again, the graph neural network so far, I don't have a class in which it doesn't work. So the only part that maybe is that the strong branching is considered to be the best heuristics, but there are some classes of problems in which strong branching doesn't help you very much, which, for example, is the class of knapsack, multiple knapsack instances. And that the one that you try to, of course, learn from strong branching, the expert is bad, so you don't learn anything really. But the graph neural network can still be effective if you could learn from something else in that particular case. I think you can still learn by graph neural network, probably not strong branching, because that's not a good expert. Yes?
And can you classify, like, you know, I give you an image like this, whether it's like a research
Potentially, I think you can. I think you can in some extent, and I think that would be one way. So this is the other catch that I was talking about in order to move from solving from implementing ideas from learning into MIP solvers. They currently don't do that. They don't classify. I mean, they do in the pre-processing phase. They do a little bit of learning on what is going on, but not at the level of deciding branching of this type. Yes.
So the graph neural network has certain challenge in handling long-range interactions. So could this suggest that the strong branching heuristic actually is pretty local? I mean, in reality, I mean, maybe, I mean, the spares itself may not be, but then when you apply to all of these graphs and so on.
I think the strong branching heuristic is a very look ahead object. So now what is look ahead in the sense that you're trying something is a generate and test, if you think right about it. Like, I mean, I'm solving the LP and now I am observing. But what is problematic with the strong branching is that it is very local in the sense that it's just to do one step. So ideally, one you should try to do, okay, let's do 3 steps and then try to see what is the real value.
I mean, even though you're just changing one variable, the decision may require information from long range, right? I mean,
Yeah.
this, since the graph neural network works pretty well, could be that essentially local information is sufficient to make the decisions.
Yeah, it's possible.
So the expert is not the expert. If I understand how you describe strong branching, this is a kind of a local.
No, the experts still have to solve LP, right?
Yes, but solving LPs, I mean, and again, this is an interesting thing. So yesterday you were pointing out. So Christopher has a nice paper in which they show that the graph neural network can learn the interior point method, so being able to actually solve an LP. But the question is, and of course strong branching is solving LPs branching LPs in order to compute the score. Now, is it I'm not sure that this is totally the full answer, that solving the LP is the full answer. I think it's actually like comparing things is actually the full answer. Like the value of the LP together with some other component which is actually local to the thing. But I mean, to me it's a very open question to look into that, yes.
I also had a question maybe related. If there are, but maybe it's not the right time. Maybe But anyway, so the question is.
I don't have much more. I mean, it's like I have a few examples that I want to run through, but I mean, I have time. Yeah.
If there is a way to do self-supervised training of the GNNs, methods, and so on, or, you know, because you said in some, like before you said in some instances, strong branching is not that, is not really an expert. And
Yeah, because my intuition is because in knapsack instances, the change in the LP that you are obtaining by branching on a single variable is too small to discriminate the quality of the variables. And then the expert is just returning you noise, essentially.
So, but then there are obstructions to do a self-supervised deep learning approach for that? No.
Probably not. No, I don't see that.
In theory, one can.
Yeah. So, yeah. So this is the reinforcement learning. I mean, now this brings us out of the graph neural network thing, but partially at least. So whenever an integer programming person talks about branching with somebody in machine learning, it immediately comes to mind reinforcement learning, right? I mean, it's like it's a sequential approach. You make a decision, you collect a reward, and so on. So why is reinforcement learning is still really like it in baby steps in integer programming? Because the game of Go ends in 40 moves at most. The game of integer programming ends in millions of moves, right? I mean, it's like I do a branching, which is like a move in Go. Is it good or bad? I mean, I will probably know it. First of all, I don't even know if I will ever know if it was good or bad. But maybe I will actually be able to record some signal down the line after thousands of nodes. I mean, very hard to do. So there is some work on this recently, like taking some, let's say, using some experiments on controlled experiments on, for example, giving the optimal solution value right away and building some special trees. But this is actually very hard. Yes?
So what you just said, your third paragraph says that progress was made using supervised learning, using BNB tree evolution. But aren't you trying to make your GNN better than current methods, which is BNB? So how do you make it better if you're limited by the data that you're collecting from BNB? So how is it going to be a better expert?
Well, because, I mean, here, so this is actually, first of all, these are the paper by Zarpellon and co-authors. So this is actually not this is not using a GNN, actually. This one is really like using, as far as I remember, but I mean, it's like this is using more the information on the branch amount tree and not the structure of the problem. Certainly it doesn't use GNN in the sense of the A matrix representation. So, I mean, is using imitation learning, so supervised learning, in order to say, well, I generate a bunch of branch and bound trees and I try to learn from the good ones versus the bad ones, right? I mean, it's like I have examples of good decisions that led to short branch and bound trees, bad decisions leading to long branch and bound trees. So what I'm learning here is I'm looking at the full realization of the thing, and then I go back, collect data on this, and then I go back and I try to see if that influence was not very local on a single variable branching on the LP, but on the entire branch and bound. So now, is it we still try to learn only the variable selection. We're not trying to learn a better algorithm for doing branch and bound, right? I mean, that's the most that we can learn is if variable selection, the best variable selection over realizations of a branch and bound. Yes?
Quick clarification, when you do variable selection, do you do it like several variables at a time?
I look at all the variables and I select one single variable to branch on next.
So why don't we select 2?
Well, I don't know how to I mean, that could be associated with the idea of
I mean, you get combinatorial more choices, right? It's n choose 1, n choose 2, n choose k. But suppose you have the memory to store it. Wouldn't that lead you to faster?
You mean branching at the same time on 4 possible configurations related to the 2 variables?
Yeah. And also because you mentioned why RL doesn't work is because you need to solve a million steps, but because you only branch at 1 variable per step.
Yes, that would be very hard to implement in the current solvers, but yes, it's a reasonable, I mean, it would be an interesting thing to do, yes.
Also about the million steps thing, I mean, I don't know if what you said before applies to now, because before you were saying something like, if I try on small size problems, this generalizes well with size. So you don't maybe need the million steps there in the smaller problem, and then you can generalize to the larger size.
No, I'm trying to learn something a little bit small, right? I mean, it's like I'm trying to learn if that variable is has a impact on the LP, and so having an impact on the LP is a local situation. So I claim, my personal opinion is that on a large problem or on a small problem, this is going to be the same. Now, what I'm trying to say is that for reinforcement learning, I can even, maybe the variable selection yeah, maybe I can try to learn by reinforcement learning what is the variable selection, which is good, then I can, if it's just a variable selection in terms of the quality of the LP that I obtain right away, I think it's I don't know why I should do it by reinforcement learning, while the big step will be defining the impact of branching on a variable on the overall branching boundary. I think that will be the big step.
It doesn't generalize by size.
I think the problem is that I can give you small instances in which the number of branch and bound nodes will be still very high. So I don't get that such a big difference in that sense. So now, there is a lot of work, of course, on cat selection, which partially uses neural networks. I would like to close here in 1 minute by telling you what is actually has worked so far in terms of pre-processing and configuration. So this is the area in which there were the so-called low-hanging fruits. So there are some decisions which are made only once at the very beginning, or relatively few times, that you can model as machine learning approaches, and somehow using methods which are not computationally intensive, not going back and forth from GPU to CPU to GPUs, and for this reason this has been already effective. So the first paper on this line has been this one, in which what we did is deciding. So it's a slightly more complex than, slightly larger than mixed integer linear program. So you have in mind the same model, but there is an objective function which is quadratic. And then it's very well known that in many classes of these problems you can transform this into a mixed integer linear programs if the variables are binary, by exploiting this characteristic. And so the question was, should I do it or not do it, right? I mean, which one is actually best in some circumstances? And this paper shows that there is actually you can, with a relatively low-hanging machine learning, you can decide statistically what is good, and this is implemented into the solvers. Now, routinely done in many other things, like which simplex pricing you use, pre-solve characteristics, cuttings, and so on. So this is actually something that works in practice already in the solvers. I covered this one. I will not cover this. There is some software available if you want to play with this. Yeah, I would finish with this slide, which says essentially two things. One, which I already said. So one challenge so far is this, the GPU, CPU perspective. Now NVIDIA is pushing out some GPUs which have a larger, let's say, memory for this data transfer. So maybe there is a chance over there. One opportunity which I think is very relevant in this area is the following. So currently the MIP solvers are increasingly using the concept of restart. So instead of just having a single branch and bound going from that I described before, they kind of reset occasionally if they see that the solve is not going well, right? I mean, it's like they kind of say, well, there is something going on here, I will never converge in the time limit that you gave me, so let's just reshuffle things and restart by keeping some information from the past and restart. This is something that we see more and more happening. And I think this is a great opportunity for learning because you are in this way collecting information on the fly. And that this could be potentially like a very nice way of doing things. At the moment, I think that the solvers are just have some knobs to play with, and they say, well, since the bound didn't move, I'm going to be more aggressive in cuts, I'm going to do this, this, and that, but they don't really keep all the memory of what they did. They don't analyze it, and they don't make decisions out of that, except for very simple decisions. Yes?
Previously you said that there were online models and offline. Were the online models dynamic learners? Like they...
Yes. So in the branching side, there are dynamic models that are actually online, and they observe. They more or less try to emulate this pseudo cost idea. So like they collect the pseudo cost and then they actually do some additional, instead of averaging the pseudo cost from the previous iteration, they do more complicated computation in order to decide which variable to branch on later. And these are instance specific, right? I mean, they don't care about anything that the class belongs to the class.
Are they better than the offline ones?
Not really, but the offline, if you allow yourself to work with a family of instances like traveling salesman, I think that the neural networks, graph neural networks, are still doing the best that you can do for branching, for sure. Okay, thank you very much. Making it a general thing after coffee. But yes, go ahead.